Let's talk about the different kinds of tests that we can do in statistics, and especially the ones we've been talking about in section C. First of all, we have a t-test for the mean. To make things really clear, there's a testable statistic. It's called a t-value that is calculated using this formula, and this explains the different parts of the formula. That t-value is then plugged into a distribution formula, this TCDF function, with a number of degrees of freedom to tell us a test statistic, or p-value. So just to make sure that we're really clear, we have a t-value, which is our test statistic. We plug it into this TCDF, which is our distribution function, and it gives us a p-value, letter P like Papa. And that p-value kind of tells us a probability that we use to determine our statistical significance. So generally, a p-value less than 0.05, I don't have a pen here, so I'm going to write it with my mouse. It looks terrible. If p is less than 0.5, then that is kind of the threshold, at least for this class, where we are accepting our alternate hypothesis. And if it's greater than 0.5, we're rejecting our alternate hypothesis, and we're thinking that maybe our null hypothesis might be more accurate or more evidence towards that. Okay, so there's a couple of different types of tests. We can see this is for a mean, and a mean value is going to be, in mathematics, we're looking at an average. So if I say something like my height, or the height of a whole bunch of people is around 5'6", that's an average, right? That's a mean. Whereas a proportion looks a little different. A proportion is generally given as a percentage or one thing out of another thing. So a proportion is always going to be between 0 and 1. I suppose you could have weird situations where it might be more than 100%, but that would be abnormal. And proportions are represented a little bit different, usually with a theta. And we also have this idea of a test statistic. In here we're using a z-score that's calculated by this formula. And then we use a norm CDF, which is another distribution function, to tell us a p-value. So let's talk about how we know when to use left tail, when to use right tail, based on the wording of our questions, or maybe when we have a two-tailed test. So I'll grab a couple of examples here just so that we can use them. So here's this example from one of our in-class assignments. You can read through this question, but I can read it too, so maybe I'll just do that. According to the Morning Consult in February 2020, the presidential approval rating among registered voters in Alabama and Missouri was 62% and 52%, respectively. So we're saying that there were also 1,000 respondents in each state. Can you support the claim that the presidential approval rating among registered voters was different in Alabama than in Missouri? Okay, so a couple of key things to look at here. First of all, we're looking at percentages. So this is a number of voters out of 1,000. Here, this would be 620 voters out of 1,000, 62%. If you don't understand that math there, 62% is 62 out of 100. And like I said, I'm writing with my mouse, so this is terrible. Which would be the same as 620 out of 1,000. We're assuming there are 1,000 total people. And then we also have another proportion, which is 520 out of 1,000. So we have two proportions, and we're asking if they're different. Are they different? So what are we really asking here? Let's go back to our resources sheet and see which one of these tests we're doing. Oh, okay, so we're talking about a proportion, and we're asking if they're different. So the null hypothesis, in every single case, will always have an equal sign. The null hypothesis is that the mean is not changing, it's staying the same, or the proportion is not changing, it's staying the same. So we're saying, does proportion 1 equal proportion 2? That's our null hypothesis. And to test that theory, we're going to use this fancy statistic here, where the numbers are all explained down here, what they're represented by. So these thetas without a hat on them are the actual proportion for the population, and the test statistic is using our given sample proportion for the population. Right, so if we go back to this guy, our theta hat 1 is going to be 620, and our theta hat 2 will be 620 out of 1,000, or 62%. And our theta hat 2 will be 520 out of 1,000, or 52%. And at this point, we're just going to plug and chug, plug it in to this formula. And now we decide, are we using a left tail or are we using a right tail? How do we know? And that is a very good question. Let me set it up for you. All right, so as we said, our null hypothesis is that the approval ratings in Alabama are the same as in Missouri. So theta 1 is the same as theta 2. And the alternate hypothesis is the opposite of that. In this case, we're saying, are they different? Different. Are they different? So are they not equal? I want to look at this on a number line, which I'll take a second to draw for us here. Okay, and so here's a number line. And let's imagine that this is 0. And this is 1. And here's our whatever percent that is, 62%. And here's our 52%. Did I get those numbers right? Let's make sure. Yeah. All right, so we've kind of drawn the numbers on the number line. And our question is, if this theta 1 is different than this theta 2. That's our alternate hypothesis. Is theta 1 not the same, it's really hard to do this without a pencil, as theta 2? So on the number line, if we look at where theta 1 is, I want to ask the question, and we'll use a different color, maybe yellow, to highlight. Where on the number line is not theta 1? So let's just focus for just a second. Instead of focusing on theta 2 and the 62%, I want to know where on the number line is not theta 1. And the answer is everything that is, wow, that's a weird looking pen. Let's use this one again. And we'll do it in purple. Everything that is not right on this dot right here, so not at 52, but it does include over here, and it does include over here. So if you're shading on a number line not equal to 52%, which direction are you going? And the answer is both directions, everywhere that isn't 52%. That's why when we're asking a not equal question for our alternate hypothesis, we will be asking a two-tailed test. So we're doing a two-tailed test here with a not equal symbol. So now I want to ask a different question and get a look at what that looks like. But first, just to make sure we're really all the way on the same page, with a one-tailed test, let's imagine that your distribution looks kind of like this, and your z value, here's your mean down the middle, and your z value is maybe right here. So let's say z equals 1.7. And if you are asking a two-tailed test and you get a z value of 1.7, that two-tailed test is going to look like this on one side. And since this is symmetrical, you're also going to include everything less than z equals negative 1.7, which is over here. So that's a two-tailed test. It's symmetrical, and that is why you can multiply your one-sided or one-tailed test by 2 times 2 to get the actual result of a two-tailed test that is testing on both sides. Right? Okay, so now let's do what a one-tailed test looks like. So let's look at this problem right here. You can read it to yourself. I'll read it as well. A tourist agency in California claims the mean daily cost of meals and lodging for a family of 4 traveling in California is at most $268. At most. So let's draw a number line before we do anything. First, we're talking about a mean here. That's a value. It's not a proportion. It's not 268 out of 1,000 or 268 out of 500. It's just a value. So we're talking about on our resource sheet, we immediately know we're on this page. We're talking about a mean, right? So you're going to see a TCDF when you get your test statistic. And on the number line, let's draw this 268. So just to use a little kind of circle to mean we're at 268. And let's look at the language. It says at most 268. So if I give you a number like 260, does that fall into the category of at most 268? And the answer is yes. That is not any more than 268. It is at most 268. If I give you a value of 270, does that fall into the category of at most 268? No, it does not. Right? At most 268, that excludes 270. That excludes anything bigger than 268. So if we're to draw this, it's anything less than 268. So our mean, we can call it X bar, is less than 268. Right? And you can see now that we know that this is the case, our mean is less than 268. When we draw our test statistics, we'll use the reference sheet to plug in the numbers and do our calculations right here. We plug in the numbers, we do our calculations, and then the question is the alternate hypothesis here. So this is alternate hypothesis, is that X is less than 268. That would also mean that our null hypothesis is that X is, in fact, equal to 268, right? Or you could also look at it as 268 or greater. Those are the same thing statistically. Don't get confused there. The big deal here is when we do our test for the alternate hypothesis, we'll have a distribution of some kind defined by the test that you did, this test right here. And then that distribution will give you a z value, or a t value, excuse me. Did I say z? I meant t. A t value. And that t value is going to be tested with a one-tailed test to the left, just like on the number line, just like this verbiage said, less than. We know we're going to test to the left. So whatever our t value is, let's say it's negative 1.6. Not a great sketch, sorry about that. Negative 1.6. We're going to test to the left. So our TCDF would be negative infinity to negative 1.6, if that were the t value. Likewise, every time we have a less than symbol, it will be a left-sided, one-tailed test. So to say that again, a less than symbol in the alternate hypothesis is always a left-sided, one-tailed test, just like this. Until we get to chi-squares in section D, and that kind of breaks those rules a little bit, but that's a different kind of test. So if you're going to sum this up into rules, if you say you have a not equal in your alternate hypothesis, that's a two-tailed test. If you have a less than, it's a left-handed one-tailed test. If you have a greater than, it's a right-handed one-tailed test. Hopefully that helps make sense of all that.